So the next step in understanding a bit more about chemistry, especially as it relates to biology, is to understand why atoms or chemicals interact and do chemical reactions when they do. And one thing to think about here is that atoms really want to become stable. And for an atom to be stable, it needs to have a completely filled valence shell of electrons. So you can think of atoms as on a mission through the universe to try and get to a point where their outer shell is full of electrons. Now on this slide here, you can see, let's see, there's hydrogen right here, sulfur right here, aluminum right here, and sodium. And these are Lewis diagrams. So we can see the valence electrons for each one. And for each of these atoms, they are not stable. So let's look at sulfur, for example. Sulfur right here. Sulfur has 1, 2, 3, 4, 5, 6 valence electrons shown here. And so the full shell would have 8, not 6. And so sulfur is not stable yet. Here's aluminum down here. So aluminum has got 3 electrons. This shell can also accommodate 8. So again, this is also not full. And then finally, sodium down here, it's only got 1 valence electron in its outer shell. So this shell's got space for 7 more. It's also not full. So, and even hydrogen. Hydrogen's really tiny and it's only using the first shell. But the first shell can hold 2 electrons and there's only 1 in it. So again, not a full shell. So none of these atoms are stable currently. They're not happy. They are on a mission to try and get a full shell. So they can do one of 2 things to get a full shell. They can either try and scavenge up electrons from someplace else to fill in the gaps, or they also have another option. So if you think about sodium here, it's got 1 valence electron, but back in behind that, there's other shells, right? There's 2 in the first shell, 8 in the second shell, and then 1 in the third shell. And here we're just seeing the third shell. But if sodium was able to offload that electron somewhere, get rid of it, toss it away, then that shell would be gone, and the outer shell would be the shell that was won back, which was actually full of 8. And that's good because that is a full shell. So there are options. Atoms can either try and gather up electrons to fill a shell, or they can try and shed electrons to completely empty out their outer shell so they can go back to the shell behind it, which is already full. They're generally going to pick whichever is the lowest number of things to do. So for example, sulfur. If we look at sulfur again right here, sulfur can either try and pick up 2 electrons, 1 to go here and 1 to go here to make this a full shell, or it could try and throw away all 6. So what's it going to do? Is it going to try and throw away 6 or find 2? Well, 2 is probably easier than 6, so it's going to try and find 2. Aluminum, on the other hand, it's got 3 electrons. So to get up to 8, it's either going to have to find 5 more, 1 here, 1 here, 1 here, 1 here, and 1 here. So it could try and find 5, or it could just try and throw away 1, 2, 3. And again, I think 3 is going to be easier than 5, so aluminum is going to try and throw away electrons rather than try and find many more. And same with sodium. Sodium could try and gather up 7, or it could try and throw away 1. It's going to try and get rid of the 1. And once these atoms have done those things, they will be considered stable. All right, so let's move on to this next slide here and watch what's going on here. So here we start off with 2 atoms, an atom of sodium on the left and an atom of chlorine on the right. And the little dark gray things that are flying around the outside, those are the valence electrons. Sodium's got 1, chlorine's got 7. So when they get close to each other, these 2 atoms, we can see something happens right there. Let's watch it again. Something happens there. All right. So if you think about in your head what you just saw happen, sodium gave away its 1 valence electron and chlorine picked it up. So sodium just had one to get rid of. Chlorine is searching the universe to find one electron. This is like a match made in heaven. Chlorine's like, where have you been all my life? Just give me that electron. And sodium's like, sure, I'm desperate to get rid of it. Here, you can take it. And when that happens, sodium ends up with a full outer shell and chlorine ends up with a full outer shell. But one other thing happened too. If you look really closely here, we go from sodium to sodium plus and chlorine to chlorine minus. So as soon as an electron is transferred from, one atom to the other, the atoms suddenly gain a charge. They're neutral and then now they've got a charge. They're neutral, 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 now they've got a charge. So we're going to talk about why that happens on the next slide. So close up, looking at what was going on in that animation, here's a sort of rough Bohr diagram showing sodium with 2 in the first shell, 2 electrons in the first shell, and 1, 2, 3, 4, 5, 6, 7, 8 electrons in the next shell, and then 1 valence electron up here, shown in pink. And here's chlorine with its 1, 2, 3, 4, 5, 6, 7 valence electrons, and the one that's kind of missing or that it's trying to find. And they start off with no charge. Look, sodium, no charge, chlorine, no charge, and they're called atoms. When they have no charge, they're called atoms. Then they encounter each other, and sodium is super excited and happy to offload its single electron, and chlorine is super excited to accept it. Now sodium has a full outer shell, and chlorine has a full outer shell. But sodium now has a positive charge and chlorine now has a negative charge. And now they're called ions, not atoms. So if we backtrack and think about our definitions, atoms do not have a charge. They cannot have a charge. The number of protons and the number of electrons is always equal. And in fact, over here, there are 11 protons and 11 electrons in this atom. And over here, there are 17 protons and 17 electrons. Now, if we go to this diagram on the right, I did nothing to change the nucleus. So this nucleus still has 11 protons in it. I haven't changed that. And this nucleus still has 17 protons in it. I haven't changed that. Now I'm going to change color. That blue is really hard to read. Let me get rid of that. I'll go back to red. So we haven't changed the center, the nucleus. We've still got 11 protons there, and we've still got 17 protons here. What we have changed, though, is the number of electrons. Sodium lost an electron. It gave it away. So now there's only 10 electrons left out here. And chlorine went from 17 electrons to 18 because it picked one up. So if we compare these two numbers in sodium, if you compare this number and this number in sodium, it has 11 protons and only 10 electrons. So it has one extra plus compared to minus. And that's why we say sodium now has a positive charge. Chlorine, on the other hand, so sodium down here, look, has a positive charge now. Chlorine, on the other hand, still has 17 positive protons, but now it has 18 negative electrons. So it has an extra negative compared to positive. So we're going to say chlorine has a negative charge. And now we call these ions. All right, so once again, the charge on the ion, whether it's positive or negative, isn't whether it picked something up or whether it lost something. That's not what it's talking about. It's talking about at the end of all this trading around of electrons, is there an imbalance, and are there more positives than negatives, or there are more negatives than positive? Which way around is it? And anytime something gives away electrons, like sodium did, it's going to become a positively charged ion. And anytime something gains electrons, like chlorine did, it's going to become negatively charged. And we have some general terms here. If something has a negative charge, we call it a, if something has a positive charge, we call it a cation. So anything with a positive charge is considered a cation. So C-A-T-I-O-N. It's easy to remember because look, there's a positive charge right in the middle of the word. That T looks like a plus, right? So cations are always positively charged. The opposite of that is an anion. Looks like onion, which makes you cry, so it's negative. So these are negatively charged ions and these are positively charged ions. Anything that's a positively charged ion you can call a cation. Anything that's a negatively charged ion you can call an anion. And although these particles now have a charge, Na plus or Cl minus, they are actually more stable than when they started because their outer shell is now full, and that's what they want, is a full outer shell. So this little thing along the bottom here is kind of describing that for you, that atoms might be neutral, but they're not necessarily stable. Ions, on the other hand, have a charge, but that makes them more stable because their outer shell is now full. All right, so the one last little thing, and I love this example of sodium and chlorine. So here's a picture of sodium. Sodium it's very rare. You're not going to see it out on the street. It's a very reactive metal. It's very soft. You can cut it with a butter knife, and this person here is wearing gloves. If you drop this into water, it will explode. It will burn your skin. You never find it out in nature. It's super reactive. And the reason why sodium is super reactive is that it's just going around the universe desperately trying to find something to take away its single stupid electron in the outer shell that's messing up its stability. So sodium, crazy reactive, will kill you if it wants to, and trying to get rid of its electron. So chlorine. There's a picture of some chlorine gas in the next picture. Chlorine's a green colored gas. It's used to sterilize and clean things. If you're in a pool and stuff, it's toxic. It's dangerous. It will kill you. It's a nasty, nasty, nasty gas. Not safe at all. So we got sodium atoms, super reactive, explosive, toxic, not nice. Chlorine atoms, super toxic, kill you, not very nice. All we do is take one electron from each atom of sodium and transfer it to an atom of chlorine. The sodium goes to Na plus, the chlorine becomes Cl minus, and you've created sodium chloride. What is that on the far right? It's table salt. That's the stuff that will sit in your pantry for 10 years and still be salt. And you can put it on your food and you can eat it and it's completely safe and it's not going to harm you. I mean, unless you're eating vast quantities of it when it can screw up your blood pressure, but that's kind of separate. It's really not poisonous, right? So although salt has sodium in it and chlorine in it, it's not sodium atoms and it's not chlorine atoms. It's sodium ions and chloride ions, where the outer shells of those particles are now full of electrons, and it becomes super, super stable, and it doesn't behave like sodium anymore, and it doesn't behave like chlorine anymore. It behaves like something completely different because you have changed the structure of the atoms that make up that substance. And that's really fundamentally what chemistry is: moving electrons around between atoms to create particles that behave in different ways. It's pretty amazing.